How do we smell things differently? Everyone has very distinct smells that can often trigger memories, like cookies reminding you of grandma, or the smell of rain reminds you of your younger years as you splashed around. But how are we smelling all these different things? What makes these smells differ? Why do some things have a smell and others don't? Well, to begin, let's talk about what we are smelling and how it gets into the air. When a person takes a breath in and smells something, it is because different molecules that are in the air are now entering their nose. Once there, the mucus inside their nose begins to dissolve new molecules and ultimately sends signals to your brain.
A good follow-up question to that would be, well, why do smells differ? Well, a different smell will come from different molecules. For example, O3 will give you a different smell than a long carbon chain. Now the next question might be, well, how are these molecules just in the air? Well, now that we know that different molecules can have different smells, let's discuss how they get into the air around us. Some molecules do not have a strong force holding them together, so often just a little bit of energy is needed for the molecules to break apart from each other. Then we have factors such as wind that can blow the molecules up to our noses. For example, long carbon chains do not have a strong dipole force. This means that there is not too much holding the molecules together. This is due to electronegativity. CC bonds and CH bonds are relatively nonpolar since the electronegativity of carbon and hydrogen are quite similar. This would change if we had a molecule with stronger forces holding them together. An example of this would be H2O, aka water, or basically any other molecule that can hydrogen bond with itself. These have very strong dipole forces holding them together, and these molecules are all connected with strong hydrogen bonds that require a lot of energy to break.
An example that relates back to organic chemistry is caravone. Caravone is a very interesting compound because it can have two different smells while still having the same physical properties. The smell depends on whether the R enantiomer or the S enantiomer is present. These two molecules are mirror images of one another and are not superimposable, much like your hands are to one another. Your feet are another example. To help drive this point home, think of chirality in your gloves. While they may look identical, we all know that our left hand will not fit into our right hand glove. Same goes for your shoes. Your right shoe does not fit onto your left foot. Well, not comfortably, that is.
To determine which one enantiomer is given, the individual must first find a chiral center. A chiral center is a carbon that is connected to 4 different groups. Here are a few examples to aid you in understanding what it means to have a chiral center. You may press pause on the video here and determine what molecules are in fact chiral.
This carbon does not have chirality because it is connected to 2 hydrogens. Therefore, it is not connected to 4 different groups. None of these carbons have chirality because they are all connected to other carbons and hydrogens. Therefore, there is no 4 groups in this one either. This carbon does not have chirality because it is not connected to 4 groups. It is double bonded to this oxygen and only bonded to 3 groups. This carbon is a chiral center because it is bonded to 4 different groups. This molecule has one chiral carbon center, and it is this one right here because it is bonded to 4 different groups.
Now determining R and S. Rank the 4 groups surrounding the chiral center based on atomic weight. Once that is determined, the individual must then look down the bond containing the highest ranking atom in the chiral center. Using your rankings, determine if you are counting in a clockwise motion or a counterclockwise motion. Counterclockwise is S and clockwise is R. See if you can determine R or S on this example.
Using this example, we can see that we have a chiral carbon here in the center because it is bonded to 4 different groups. So now we must prioritize the atomic number. Here we know that bromide has the highest atomic number, so we'll give it a 1. then chlorine, then fluorine, and hydrogen being number 4. Considering that hydrogen, the highest ranking group, is already facing back into the plane, we can then determine configuration based on this Lewis structure the way it is already drawn. So we can see that we're counting 1, 2, 3. We're counting this in a counterclockwise motion. Therefore, we are looking at the S configuration.
Here I have ranked and labeled the groups surrounding our chiral centers. Now you can see why one is R and the other is S. This is a truly fascinating piece of information because according to certain research, this can serve as evidence that our noses are actually chiral, and thus the reason we can detect the difference between the two molecules. Our sense of smell is amazing and allows us to smell over hundreds of different smells. Now, science is here to tell us that some molecules are actually producing different smells. This proves that many olfactorants are also chiral and certain molecules fit into certain receptors. A certain way of thinking about this is going back to the right hand fitting into our left-handed glove. It simply would just not work. Ultimately, this is a short video on how we smell different things. Thank you for watching.